Welcome everyone. In today's class, we are continuing our discussion on hardware efficient C coding. So, as we discuss this hardware efficient C coding, we try to mean that we sometimes we write our code without understanding how it will be implemented in hardware. We may end up getting a very hardware which is not efficient at all, right. So, in this class we try to understand what are the things we should consider during writing the C code and then converting into hardware. Okay. So, we have already discussed about this efficient coding for array and loops. Specifically for array we have discussed many things. Specifically the array access is a bottleneck for hardware realization of a C code, and also in the previous class we have discussed various construct which is not getting supported in during hardware synthesis. We have also discussed that, and also another important aspect that we have discussed is this precision, that the data width. In general our data width is 32-bit, 64 int, float and all, but in hardware you can actually have any arbitrary precisions and how to make utilize of that, because otherwise our this area will be too much, right. So, we have also discussed that part. We have also discussed about the function, how the function gets implemented in hardware, and specifically this hardware, how this resource sharing and is done when functions create a separate module. So, we have all discussed those things in detail. We also discuss about the array initialization, because array initialization is something create a lot of latency if you do not take care of them properly. And also we have discussed about this, we keep array as a function, top level function, we just put array as the argument, right. So, how it will get reflected in the hardware and how that gets managed. So, those things we have already discussed in detail, right. So, in today's class I am going to discuss primarily 2-3 things. One is basically there are some common construct like static, const, global variable, pointers, how they gets reflected in hardware. Also I am going to discuss about another important topic, which is this dependency, right. So, the dependency can cause lot of problem in loop pipelining. So, we are going to discuss with some examples how the dependency is causing problem, and at the end I am going to discuss about how we can improve the latency by just taking care of some minor thing in the input C code. Okay. So, let us start with this type qualifiers, right. So, we have used this static, const, those things in our program at a lot, right. So, what about the static? So, you know the static variable, which is something if it is defined within a function, its scope remain within the function, right, but its lifetime remain across the complete program execution program, right. So, that means if I visit the function multiple times, whatever the value it was there previously, it will start with that value, right. So, there is a very nice example here. So, suppose I have a function called func, where I am just having a int count and then I am just doing count plus plus and returning the count. Okay. So, what I am done here in the main, I just call func, right, and then I call func again. Okay. So, what is going to happen? So, if you call first time your count is 0, then count become 1 and it will return count. So, it will print 1. You call second time, again count is 0, because you call second time count 0, again it will become count equal to 1 and return 1. So, it will print 1, right. So, now if you just put static int, if you make it static int, then what is happen? For the first call you come, count is initialized to 0 and then become count equal to 1 and return count. So, it will print 1 here. For the next call it won't execute this, because it is only initialized once, right. So, next time it will remember the value of this count, it was 1. So, it will do count plus plus equal to 2 and it will return 2 and it will print 2, right. This is for static and this is for ordinary, right. So, this is what is the static, and sometime it is important to utilize static in our program, because sometime we want to keep this old value remember, right. So, now you think about this normal variable, the ordinary variable versus static variable, how they gets mapped into hardware. So, for the ordinary variable here, what I can do, I can just this count may not be stored in some register, because I can just do what I just because this count equal to 0. So, once I realize this, it will always say return 1, right. So, this function I can actually do a constant propagation and I can actually return 1, right. So, what is going to happen in the ordinary case, I do not have to store this count in a register at all, right, but for static this must be stored in a register, right. So, you have to store in register, because if it is register it will initialize with 0, and then whenever you call it, it will do that count plus plus, right, and it will give you the extra value. And because in hardware all modules are actually running in parallel and they will remain live for throughout the execution of the program. So, whenever you call second time, it will actually return you the modified value. So, the basic point that I try to mention here is that for static variable we have to realize this using a hardware, and it must be initialized, right. So, the whatever the initial value, it may be 0 or it may be some explicit value. Instead of 0 you could have count to 10 also, right. So, you can initialize this 10. So, then next time it will 10, 11, 12, 13 and 14, right. So, so basically it has to be explicitly initialized and it must be stored in a hardware in a register, okay. And for FPGA bitstream also it has to be initialized during the loading of the bitstream. So, this is a simple thing, but you should understand how this ordinary variable versus static variable get realized into hardware. So, now there is a const. So, we usually use const int, right. So, or const int some value. So, by default if you do not specify anything, the default value is 0, and if you specify, then this value b value remain 12 for throughout the program, right. So, it is basically read only, const is basically read only. So, if it is read only, so the basic idea is that if it is a array, read only array, then it will be a ROM, right. So, this is if say array, it will be mapped to ROM, and if it is a variable, read only variable, then it will be mapped to a constant register, right. So, you can just think about there is a constant in the RTL which will realize this. So, this is something very simple, but I just complete this for sake of completeness. Okay. So, the conclusion is the const is basically read only aspect. So, it will be implemented as a constant register or a ROM in the hardware. Okay. So, now next the global variable. So, we all know global variable. So, global variable is something, it is basically live throughout the program executions and it can be accessed from any functions, right. So, that is the purpose of the global variable. So, in generally the how this global variable will get exposed. So, you have to understand that, right. So, suppose you have a function where you have a global variable say int a, right, and now you have a top level function, you are calling say function 1, function 2, say function n, right. So, this a is actually accessible everywhere. So, now you think about this a may be accessed here as well, right. So, a plus plus you can do it, right. So, now where this a will store in the hardware. So, you remember that once you have a function, it will create a module, right. So, every function will be realized by a module. So, there is a module for a function 1 to say function n, right. And now where this a will be stored within the functions or top. If it is get access in the top level module, this is your top level module. So, there will be say some register which is storing a, right. Now, you think about that whenever you have this a and if you want to do something here, right. So, some operation on a plus 5 here. So, you have to pass it here as an argument, right. So, it will be an argument. If you want to access this here also, you have to create an argument, right. And now, if this gets value updated, there will be argument and it will actually update this also. So, this will create some input port or output port also. It may create only the one port, because if it is only updated there, right, you are not accessing, you are just updating that value. So, suppose here you are doing a equal to 6. So, that means you should have a output port here which will update this. So, the bottom line here is that once you have a global variable with in the hardware, because it is become a it is accessible to all functions. So, it will create lot of ports, right. So, by default in at least in Vivado HLS, they analyzed, right. So, what are the functions is going to use, and if it is only local to a function, it is basically move that global variable to a local to that variable to that function, right. So, for example, if you take this example here, you have this there are 3 global variable here, a in, a int and a out. And in this function, this is the only function where this is getting used, and you see here that I am actually computing a int using a in, then I am computing a out using a int, right. So, but this is within this function. So, what is going to do it? So, this is your top level module and this is this module where that this function. So, this is this module. So, this is the module B and this is your module B. Since it identified that in the whole program these variables although they are global variable, but they are only accessed within this. So, they will move it here, right. So, this global become kind of local, right. So, if possible it will do it. So, then it will not create any port, right. So, no port will be created. So, for this function, since it has only one port, it will actually create only one port for IDX, right. So, for this example as I mentioned here, it will get only one port IDX and it will move this A in as an internal RAM, A out also internal RAM, right. So, so in this particular case it will not create anything because now this all this A in, A int and A out all become RAM in that, right. So, the point that I try to establish here is that for global variable, if I declare a global variable, ideally it will create lot of extra ports, right. So, lot of communication among these functions and lot of ports because it can access, right. So, wherever it get access it will create port, but if it is local probably high level synthesis tool can move and make it local, although you have declared it as a global variable. But whenever there is a array, you understand that it is not a single port, you have to create 3-4 ports. It is a read address port, data port, data in, data out port, as well as the write enable and clock enable. So, now you think about there are say 5 such arrays are getting you have declared as global, it will create lot of unnecessary ports to this to these modules corresponding to the functions, right. So, in general, so it is not recommended to use global variable, right. So, unless and until it is necessary, right. So, because it create lot of dependencies among the modules and it might actually hinder some optimizations applying of the task level pipelining. So, in general this is we should avoid this use of global variables. Okay. So, now I move to discussion on the pointers, and we know pointers is something very important functionality in C through which I can access the address of a registers or an array or a variables, right. So, it is extensively used in C and it is actually very well supported in high level synthesis, right. So, it is actually getting supported, and if you look into pointer, what is that? It is basically you are accessing a location, right. So, in hardware if you think about you have an array, you are accessing this to a pointer which is nothing but you have a RAM and you are accessing through some address, right. So, supporting pointer in hardware is basically it is easy, right. It is just nothing but having the address, right. So, you have to convert those pointer into corresponding address in the hardware, right. So, in general this high level synthesis to support all type of pointers, right. So, pointer that actually pointing to multiple objects, right. So, suppose you have in star A and then say A storing the address of P, after some time A storing address of Q. So, this type of things are supporting because it is nothing but this is a register probably, and it is nothing but A is basically it become this register, right. So, it is basically pointing to that register and here it pointing to another register Q, right. So, pointer to that point multiple objects is getting supported. Pointer to pointer is basically indirect addressing, right. So, you have this pointer, you point to some location and that actually store the actual address. So, it is just indirect addressing and it is very easy to support that in hardware, right. So, that is also supported. Array of pointers also is supported in high level synthesis because it is nothing but set of addresses, right. So, it is not difficult to support that. Even pointer casting is also supported for native C types, right. So, for example, you have an integer pointer, you cast it to point to a character type, right. So, even that things are also supported because it is just again in the hardware if you think about the casting is nothing but you just mentioning that this variable can store the address of this register instead of this register, right. So, so that way it is not a problem. Pointer casting is supported, even pointer is supported as the argument of top level function. Okay. So, basically if you think about you have a top level function and you try to pass a address of a array pointer, right. So, in integer pointer that is actually pointing to some array, even that is supported, but here we have certain restrictions. Okay, I am going to discuss this in bit detail. So, how this this argument at the top level get implemented in hardware, right. So, you now think about say suppose you have a top level function where you have a star A, right. So, you have a int star A. So, now in this particular program, so this is basically you can access this, right. So, you can actually have some for loop, you 1 to n, you try to access this A I, right. You want to access this. So, what is going to happen once you have this int pointer at the top level function, what it creates? It is basically create three types of connections, right. So, it basically either create a OR, or it will actually create some handshake or a FIFO, right. So, OR means basically if it is a OR at the interface, it means that you are going to read the data only when the data is ready to consume, or a data when the data is ready. So, basically you can have a handshaking signal, right. So, you basically have you get a data valid, in the next clock you are going to get the whatever the value is coming, it is actually get read, or you before computing this you send a signal that this is a valid data, and then you send the data and it is actually in the same clock. So, you send this data valid and the data. So, now the receiver process understand that this particular data that is coming is now valid data, right. So, you have to understand that whenever you have written a function, so this will be implemented in your top, and it will be integrated with some many other modules in a bigger systems, right. So, suppose this is taking A from this function. So, this may not produce this A in every cycle, right. So, there may be some latency for this, so latency is 4. So, that means every 4th cycle is getting a actually generating a valid data, right. So, once it is generating a valid data, it has to told that. So, this is A valid, right. So, that means whenever this A valid is equal to 1, then only whatever data is here, that is going to access here. So, this is OR connection, but that is something handshaking is happening, right. And now, if this so if it is a array, it is only read access, right. So, this is only read only, right, or you can have another say access say int star B, where you are just doing this bi equal to something. So, you are actually writing something to bi, right. So, that means the write only, and you can understand that they are actually accessing in order. So, both are accessing in order, order in the sense you can understand that I am not accessing randomly to this location, that means I am accessing 1, 2, 3, A1, A2, A3, A4 and so on. Similarly, I am accessing B1, B2, B3, B4. So, this is in accessing in order. In that case, if it is only read only or write only, I can realize this kind of connection as a FIFO, right, first in first out kind of connection. So, instead of this handshake, what I am going to do it now, I can actually do this, right. So, instead of doing this handshaking, that valid and all between these two modules, what I am going to do, I am actually having a module here which is my top, and say it is actually getting this A from here, right. So, what I am going to do it is, instead of making this connection direct, I am going to put a FIFO here. This is FIFO, first in first out. So, the whatever the order it is going to read it, and the same order I am going to read it, right. So, now this is my A. So, now what is going to happen because of this, now this become asynchronous, right. These two model earlier the diagram that I have drawn, it is basically synchronous, that whenever this data valid signal comes, it has to consume that data, right. But here this particular module can actually generate in any different clock the data into this FIFO, and this guy can read it in its own space, right. So, it may produce in every cycle and it might read it in every 2 cycle, right. So, every cycle. So, this is possible because you do not have to make a explicit handshake between this access. So, in such kind of cases, whenever you have this, so this the high level synthesis tool analyze whether this access is in order, because so unless this read and write is in the same order, you cannot do it, right. So, you can only realize FIFO if it is only read only or write only, right. So, if you are read and write both from the same FIFO, you cannot realize, I mean from the same array, you cannot realize that particular array as a FIFO, because FIFO you understand first in first out. So, the order it is going to be data is written, this module is going to read it in the same order. So, in the sense that if you do not have this order, same order things are there, you cannot do it. And also this guy only can write it, read it from here, and this can only read. So this, if this particular array is both write and read from the same module, this won't be implemented as a FIFO. Okay. So the point here is that once you have this access, so based the tool, high level synthesis tool will analyze whether it is a read only or write only, right, and it is the access random. So are you accessing like A1, A2 to An, or you are accessing A5, A1, right, say this is random access A1, then say A2, then say A10. So this is a random order, right. So if it is this order, it is only write only or read only, then it will automatically be converted into a FIFO. And FIFO has the biggest advantage that now these two module actually can run asynchronously. And how they synchronize effectively? By the blocking read property of this, right. So if this is empty, if this FIFO is empty, that means there is no data, this process has to wait until some data comes, right. So that is how the synchronization happen. And similarly, if this is full, if the FIFO is full, this process has to wait, right. So until some data is consumed by the consumer process. So basically in such case, whenever you have this access is read only or write only, and it is accessing is in order, it is not a random access, it is basically converted into a FIFO, and this both producer and consumer can actually run asynchronously, and they are actually getting synchronized by the blocking read property or so on and wait on full, right. So this is how this can be done. Now the point that I try to make here is that once you have declared a pointer, a high level synthesis tool either try to implement by this wire is basically I just make the handshake, the data valid things, or FIFO, right. So if it is not, if it is a random access and all, it won't able to implement that, right. So that pointer, in the point I try to make it here. So so if it is handshake and FIFO read and write should be in the same order. So what I am trying to say is that if it is not, it is not following that, it won't be able to implement that FIFO or this handshake or wire, right. So in that case, what you have to do, instead of this pointer, you should use a explicit array, right. So if you do a explicit array, what the high level synthesis tool assume, so what I am trying to mean is here is that here instead of a pointer you use a A10, right. So now the tool will understand that this is an array which is basically be an RAM, external RAM. So the tool will assume that there is a RAM is present in the SOC, which is not part of this top module, but it is a RAM, right. So what is going to access now, instead of doing this, so whenever you put it as an array, right. So what is going to do is this, that so suppose you have this top module and you have an array, right. This is your top module. It will assume, if you write this as an array like this, so it will assume there is a RAM here A, and this is a RAM, and now you can access randomly, right. So you can both read and write, both read or write, both is possible, any order, right. So both is possible because it just creates some address, right. So it will create address, it will create data, it will create the write enable, it will create the read enable and all those things, and then it will just give some address. If you want to write, it will just make the write enable, or if you want to read, it will just make sure that it is not write enable, right. So the point is that if you use pointer at the argument, it must be should be implemented by wire, handshake or FIFO mode. If it is not, you should implement that instead of pointer, you must use an array, so that this can be realized as a RAM, external RAM in the during high level synthesis. Okay. So that is all about the pointer. I will now move on to the dependencies. So data dependency is something we all knows. There are and we have already discussed during scheduling that whenever you schedule an operations, you have to make sure that the data dependency is not violated. Okay. So that is already discussed, and that is already taken care by high level synthesis, the scheduling part. Okay. So what I am going to talk about is there what kind of dependencies are there among these operations, and how the dependency can actually impact on the loop pipelining, because we have already discussed and convinced ourselves that this loop pipelining is one of the most important features of high level synthesis to realize efficient implementation of the loops in hardware. Okay. So, let us understand what are the dependencies are there. So, there are 4 type of dependencies. What is called raw is a read after write, as and this is called true dependencies. What is that? So, from the name you can understand that you are reading after writing something, right. So, you are writing something in this value t and then you are reading here, right. So, that means you are read after write, right. This is a true dependency, and this is what we have actually talked about in scheduling time also, right. This is what is the data dependencies. Okay. So, that means this t has to be executed, completion of the state t has to be there, then only this operations L I2 can execute, right. So, now we have a write after read. Okay. This is called anti dependencies. So, you are reading something, you are reading t here and then you are writing here, right. This is write after read. So, this is also a dependency that has to be supported, because otherwise if you just move this operation here, this operation b will take a wrong value, right. So, the functionality will change. So, we have to obey this write after read dependencies as well. So, there are 2 more type of dependencies. The next one is write after write. So, that means you are writing to t and then you are writing again, right. So, you cannot again change the order. This is also the dependency that has to be supported or it has to be honored during the hardware implementation. Otherwise, if you just move this operation here, the order will change and this c will get a wrong value, right. So, that means we have to obey this write after write dependencies as well. And there is one more is read after read. So, that means you are reading something, right. So, you are reading say t, say t plus 1 and then again you are reading C1 equal to t plus 5. So, here it does not matter whether I read this first or this first. So, in this case I do not have to because since the value of the t is remains same. So, in which order I update C1 does not matter, right. So, this is not something a no dependency. So, we can actually ignore this one, but this 3 is something important and has to be obeyed, right, during hardware implementation. So, now what I am going to discuss is we understand this kind of dependencies and this how this dependencies is actually creating impact on this loop pipelining. Okay. So, let us take an simplest example that suppose I have a loop here and you have a if a greater than b, then I am updating a equal to a minus b, or I am updating b equal to b minus a, right. So, suppose this is what is happening and this is within a loop while, right. So, now I want to if I want to do the pipelining. So, you have to remember that in the loop pipelining what we do, we have one iteration of the loop and then I want to I do not want to wait till the completion of that particular iteration, and I want to start the next iteration early before completion, right. So, that means if this is the time taken by the iteration 1, right, I do not want to start my I equal to from here, right. This is the normal non-pipeline version of the execution, right. So, if I equal to 2, this is the non-pipeline version of the loop implementation, but in the pipeline mode what I want to do? I want to start these things early, right. I want to start, say this is the clocks, right, this is the clock 1 and clock. So, I want to start the next iteration immediately after first clock. So, that means what is going to happen is that the 2 iterations or multiple iteration rather is going to run in parallel, right. So, multiple iterations are running at the same time, but on different set of data. So, which is good for earlier ideal case. Now, you think about the I plus 1 iteration depends on ith iteration, right. So, that means whatever the data I need in I plus 1 iteration which depends on the data of ith iteration. So, which is called is very known is the data hazard, right, in the pipeline, the normal processor level pipelining as well. So, that means for example, say I am calculating q here and that is getting used here, right. So, q is getting used here. So, that means I cannot do these things in parallel. So, I have to shift this loop at least by 1, because this is going to be it is defined in say this clock. So, I have to move these things one bit early, and so that I can actually use q here, right. So, you understand that. So, this is basically the dependency across iterations, right. So, now this actually, so earlier the diagram that I have drawn, their initiation interval was 1, now the initiation interval become 2. That means, I cannot start my next iteration immediately in the next clock, rather I have to start this things every second clock, right. So, I can start the third iteration here and so on. So, if there is such dependencies, right, across loop iterations. And this particular example is the perfect example here, because say suppose I want to pipeline this loop now, and in whatever I am calculating in the ith iteration A and B, it is getting used the first time in the checking, right. So, that means, I cannot do anything until I check this condition, right, and this value A and B will be getting at least end of this first iteration. So, it means that I cannot start the next iteration in overlap with this, I can only start it at the end of the first iteration, right. So, that means, I can only start in this particular example, that I can only start the next iterations once this A and B value is available, then only I can check this. So, this is my I equal to 2. So, this means is actually this loop cannot be pipelined at all, right, because here because of this loop carried dependencies, I cannot pipeline at all the loop, right. So, because the second iteration has to wait the completion of the first iteration. So, that is what I try to mean, that this once we have the program, we may not understand this, but I just apply loop pipeline, right, and if we apply pipeline to this loop, say pipeline equal to I equal to 1, just simply compiler will highlight synthesis so that it cannot be pipeline, I just have a non pipeline implementation. Okay. So, obviously, in this case we can't do anything, because it's very this is how the program is written, but sometime probably some tweaking is possible in the code, so that this kind of dependency can be avoided or shortened, right. So, the idea is that you try to ensure that initial operation is performed as early as possible, so that the dependency is kind of removed. Okay. So, this is what I just try to give the impact of this loop carried dependencies on the loop pipelining. Okay. So, I will take two more examples just to highlight this the same fact. So, here I have taken an example which is something, if you see here, I want to have a loop here, right, and in the loop what I am doing, I am just doing, I am reading m, when I am calculating m, then I am writing that value of m to a memory I plus 1, and I am also reading memory I to some value r. Okay. So, you now think about this scheduling. So, I can, and say let us say this multiplier is say 2 cycle operation. So, you can actually do this multiplication in 2 cycle. At the same time, because you want to write in I plus 1 location and reading from I. So, you can actually do the read operation here, right, read I am writing simply, and I can only do this write operation, write I plus 1 in once this multiplication is completed, right, because that particular value is getting written into I plus location, but this I and I plus 1 is something independent. So, this read can happen in parallel with these operations. This is the schedule I am going to get, right. So, it is basically 3 steps and I can pipeline it. If I now try to pipeline with my pipeline I equal to 1, if I try to apply my high level synthesis tool, you say that this I cannot be possible 1 initiation interval, I am going to get 2. Okay. So, why? Because if you just try to understand this here, so within the loop there is no problem, right. So, there is no issue in the same iteration of the loop, because the read index, write index and read index is completely different, right. So, I can actually execute this at the same time concurrently, whatever exactly I want to mean here. So, you can put this read here as well, both is possible, but I just try to schedule as early as possible. So, there is no problem as such within one iteration. Now, think about the loop carried dependencies. Okay. So, let us try to understand that. So, if you just think about my iteration I equal to 0, I am actually writing to location memory 1 and reading from memory 0, which is fine, there are two different locations. But in I equal to 1, I am writing to memory location 2 and reading from 1, and what is this 1? Which is getting written in the previous iteration, right. So, that means whatever the data I am going to write in iteration 0, I am going to read it in iteration 1. So, what does it mean? I have to wait for till the writing is done, right. So, that means unless this data is written, I cannot start the next iteration, because that R is also so this is going to happen, right. So, that is where the loop carried dependency is causing problem and this pipelining is getting hindered, right. So, if you understand this, so basically this is your the multiplication operation is happening and you are doing this read equal to memory 0 and you are writing to memory 1, in this is for I 0, and I can only start this I equal to 1 here, right. So, and you can ask me how it is possible, because I am writing to memory 1 and reading it here. This actually possible by data forwarding, right. This is called data forwarding. So, this is very well known technique for loop improving the reducing the data hazard. So, ideally this has to delayed by one more, and there is no pipelining is possible, right. So, you have to do this from here only, right. So, this read should come here and this also move by 1, but because this data forwarding is possible. So, I can write this M to this memory location 1 and I can directly assign this to R next, right. So, I can directly write M to this location, instead of this I just write M here. This is what the data forwarding, and with this I can actually you can understand that. So, this is my clock 1, this is clock 2 and this is my I equal to 2, because I am starting the I equal to iteration after 2 cycle, right. So, this every 2 cycle I can start, right. So, I can start the next iteration from here. This is for I equal to 3. So, what I am trying to mean is that because of this loop carried dependencies across 2 loops, it actually hindered the pipelining and I cannot achieve my initialization interval to 1 for this case, but with data forwarding I can actually achieve initialization interval equal to 2. Now, let me take some tweaking version of this example, which is a completely different functionality. So, what I am doing here is I am going to read the memory first, right. So, read I, then I am going to calculate this and then I am going to do this. So, if you remember here in this example, whatever this R is getting used, that is actually read in the previous cycle, right. So, that means I can actually there is no dependency among this within the loop, this R and this R, there is no dependencies, right. But here since I am reading it first, now I am reading this first and using it. So, there is a dependency comes here. So, how it will look like? So, now I have to do this read I ith location, then only I can start the multiplication. I can start the multiplication only after that, and once the multiplication are done, then this is going to written here. So, then only I can do this write to I plus 1 location, right. So, what does it mean? It will take 4 cycle. So, earlier example whatever I have shown, I have shown that I can actually do it in 3 cycle, right, because now these dependencies come, I cannot. So, this one iteration of the loop will take 4 cycle, and now if you think about this, that this whatever this I plus 1 written here, that is going to be written in the, this is for I equal to 0, right, and then for I equal to 1 whatever writing is happening, that is going to read here. So, that going to start from here, right, I plus 1. So, that means in general this loop is cannot be pipeline, because there is a complete this my I equal to 4, which means basically it is iterative execution, right. There is no pipelining at all, right. But only thing is that by just kind of data forwarding, I can actually read this from here as well, right, because I can just forward this data to this place as well. So, with this I can actually achieve my II equal to 3 for this example, but you can understand that because of this loop carried dependencies, this the performance of the loop pipelining is severely getting impacted, right. So, and we have to be we should at least aware of this kind of fact, that if I have code is like that, applying pipelining does not make sense in certain cases, right. For example, here this II can only be achieved 3, not 1 or 2, right, and previous case the maximum IR the initiation interval can be achieved for loop pipelining 2. So, once we write our code and try to apply this pipelining kind of pragma, we have to be careful, or we should at least aware that whether this pipelining will help you or not. In general, if there is no loop carrier dependency, pipeline give you the best performance. I can execute the loop in order of n time, but because of this dependencies, it is basically this pipeline can impact it. In some cases there is no pipelining is possible, and it will if the one iteration take k cycle, it will take k into n times, but in pipeline even if one iteration take k cycle, I can still execute the loop in n times, n clocks, right. That is the biggest advantage that we usually get through pipelining, but these dependencies can actually impact it there. Okay. So, the motivation was just to convince that sometime this loop this dependencies can actually impact the loop pipelining. Okay. So, there are certain time there is no actually dependencies, but tool cannot understand that, and as a result it cannot do the pipelining, or it actually impact the pipelining performance. So, in such cases if we see that I mean manually we understand there is no dependencies, but tool do not understand, tool not able to automatically identify that, we have to specify that this is not a correct dependency, you can ignore this, okay, and which actually improve the pipelining. So, I will take a small example quickly. So, suppose in this loop if you see I am just reading this histogram locations, I am actually reading and writing from the histogram array. Okay. So, now in general if you does not look the other part of the code, you can assume that this old and new value can be same also, right, old can be in general, right, it can be same, and then you are actually reading and writing from the same location. And so, if since this code was given and there is tool cannot identify that this I mean can actually in worst case your old and new value the old and val can be the same value, and so it is basically order this execution, it will actually write first and then read. This is basically write after read, right. So, I am actually write wire kind of dependencies. So, it will actually try to obey this dependencies and is going to schedule this write first and then next clock it is read, right. So, as a result I cannot parallelize this operations, which is correct in that sense, that is it has to be done like that, if otherwise if you just do it in parallel this will get the wrong value. But if you look into the other part of the code, so what I am doing here, if these two values is same, old and val equal to same, I am not going to do this, I am going to do something else. So, it means that if so in this case if I come to this else part, this old is always not equal to val. So, that means although there is a WAR kind of dependencies here, which is a false dependencies, because this is not going to happen in practice, because if old and val is same, I am not going to come to this part of the code. So, as a result actually it is possible to perform this read and write in the same clock, right. So, but for tool it is very difficult to analyze this kind of complex things. So, just to make sure that high level synthesis tool understand that, what you can do, you have to just specify that this pragma, that this particular for this variable histogram within that within this there is a raw dependency read after write, which is basically a false dependencies, right. So, I think I have written it is wrongly, it is basically read after write, right. So, this dependency is false dependency and you can ignore this. So, if you just specify this this particular instruction, then the high level synthesis will understand, okay, this dependency is wrong. So, I can ignore this and I can schedule this in the same clock, and that will give you the performance benefit. You can actually improve the pipeline benefit with this kind of thing. So, the point here is try to make sure that if you apply loop pipelining and if you are not achieving, you apply loop pipelining and you are not achieving what the kind of performance you are expecting because of this kind of false dependencies, then you have to just specify that this dependencies are not correct, right. So, then the tool will actually do the efficient implementation. Okay. So, now I will move to the last part of this discussion, that how we can optimize the latency in some cases. So, there are two cases where we can actually improve the latency. So, the first thing is that if there are multiple loops, we can merge into one loop so that latency can be reduced, and the second one is the flattening of the nested loop, right. So, if there is a for loop, under the for loop, another for loop and for loop. So, you understand that it is basically, if you have something here, it will be executed this, if it is n, m and l, it will execute into n into m into l times, right. And now there may be some part of the code here, some part of the code here also, right. So, if you just remove this flatten, or that means you unroll this loop and you put it here. So, these operations now can be parallelized, right. So, now the whole part of the code will execute n into m times, and this code size is big, right. So, the all L iterations code will be here, but since all code L iterations code are actually put in one iteration, then maybe some parallelism is possible, some of the operations can run in parallel. As a result, your number of iteration will be less than this, right. So, this will be much less than of this value. Okay. So, this will be lesser. So, as a result, you can actually improve performance. So, if there is a long nested loop, it is good idea to unroll the innermost loop, right. So, as a result, the parallelization will improve. As a result, the total number of clock needed to execute that particular block will reduce. Okay. So, this is one idea, and I will just take an example for merging sequential loops. So, suppose you have a loop 1, you are calculating A, and you are calculating another loop where you are calculating A again, but here the condition was di, here not di, right. So, that means these two part of the code actually mutually exclusive, right. You can just write else here and you can do this here, right. But if you do not do this, how many times cycle is taking? So, this will take 4th clock, because the loop is writing for 4th cycle, this will take 4 cycle. So, it will total take 8 cycles. Okay. But now here I understand that either this will execute or this will execute. So, I can just remove this loop and I put this as a else part, and I have only single loop, right. So, now it will take 4 cycle. So, you can actually remove one of the loop, and because this if else and is going to have is an exclusive operation, the number of operations also remain the same, and you can actually just merging such sequential loops into one loop will reduce the latency largely. So, in general, we can merge two loops if their bounds are variable and they must have the same value, right. So, if there is a for loop which is I equal to 0 to I less than n, and there is another for loop here which is j equal to 0 to j less than n. So, this condition basically the total number of time this loop will execute, total number of this loop must be the same, right. Although this is a variable bound, if they are same, then I can merge it. If there are two loops which has a constant bound, so suppose this is running for 10 and this is running for 15, still I can merge. I can only, I will take the max of this. So, I will now merge in the merge loop, I will run for k equal to 0 to 15, but I will put a conditional statement. If I less than 10, I am going to do this part of this loop, and if it is not, then I am going to do this part also, right. So, I can take the maximum count as the loop bound, but I can actually take some conditional operation, so that the operation here will not execute beyond 10. Okay. So, but if one loop is of variable bound, that means it is I 1 to n and this is 1 to 10, I cannot merge them, because I do not know the value of n, right. So, that is why I cannot merge such loops into one. And also once you merge these two code, we have to make sure that there is no side effect, right. So, that means merging together will not change the functionality of the behavior. So, we have to make sure that in such cases I can merge, and merging of the loop is very important operations, and it has to be done manually. You have to understand that this is something a manual operations, and it actually improve the latency by a large, because loops is something you have to understand that particular body is executed many times, and if you merge, the performance gain should be most of the time is huge. Okay. So, with this I will just summarize this part of the course, where we try to understand, try to convince you that writing C code for hardware, you have to taken care of various things into picture, specifically that loops, how the efficient the implementation loop is going to happen, the loop bounds, loop carried dependencies, those things you have to be very careful for efficient implementation of the loop. Array is also another important portion of the code, and it is actually have the most it's create a lot of bottleneck for efficient implementation, because this array maps into memory, and memory has a limited number of ports, right. So, for this array initializations, array interface, array access, we have to basic idea is that access of the array should be minimized and it has to be reused, right. That also we have already discussed. So, and also another important is the arbitrary precision data type. We have to make sure that my data path is actually have the there is no redundant width, which is something unnecessary creating the area. And also we should have to think about the efficient implement of the function. We should use the function judiciously, because it is created separate module and there is no kind of optimization possible across functions if they are creating separate modules. So, if the functions is rarely used, only 1 or 2 time used, or it is a smaller function, it is better to inline it rather than a function. For only function which is used many times, then only it is better to use a module for that. And also the dependencies that I have already discussed today, that the dependencies actually impact a lot of in the loop pipelining, and we have to be careful about that. If sometime this dependencies is false, we have to ignore them, right. So, these are the tricks you have to always play when you try to get a efficient hardware from C, and the more you play and the more you try, you will learn a lot of some complex part of it. I just take very simple examples, but in general there may be some very complex scenarios comes, and but the bottom line is that you have to take care of this kind of things during the C to RTL conversions. Okay. With this I conclude today's class. Thank you.